In this video, we'll look at finding the electric potential difference of a wire and use this to better understand when we'll use delta V equals minus integral E dot dr versus when we'll use V equals integral K dq over R. So let's begin by considering a long wire, but not an infinite wire. And it will have a total charge Q and length L. Suppose I want to know the potential difference between 2 points above the midpoint of the wire. What are our options? Again, I'm going to consider the length, though my diagram doesn't reflect it, to be much greater than the distance of the farther point from the wire. This will give us two options. Option one, we can compute the electric field using Gauss's law. And if you recall from Gauss's law, for a long wire, our electric field will be equal to lambda over 2 pi r epsilon naught, or Q over 2 pi r L epsilon naught. And so if point A is a distance A away and point B is a distance B away, I can now compute my electric potential difference. I'll say delta V is equal to minus integral Q over 2 pi r L epsilon naught dr. And we'll integrate from A to B. So going ahead, this gives us negative, pull out all the constants, Q over 2 pi L epsilon naught. And the integral of 1 over R will give us natural log of R evaluated from A to B. Now we can go ahead and simplify this. We get negative Q over 2 pi L epsilon naught, natural log B minus natural log A, which I'll rewrite as natural log B over A. And finally, because I don't like that negative sign out front, I can redistribute this to be Q over 2 pi L epsilon naught, natural log A over B. So that would be our potential difference between point A to point B. But could we use this same approach if we wanted to know the potential difference between 2 points, a distance A and a distance B, away from the edge of the rod? The answer is technically yes, we could use delta V equals minus integral E dot dr. But to first find E, we would need to first evaluate integral K dq over R squared. And so we'd essentially be doing an integration problem to find our electric field and then a second integration problem to find our potential difference. Instead, let's try using integral K dq over R in this scenario. So we have our rod, draw that out, and we'll begin by finding the electric potential at a distance A from the edge of the rod. And this goes very much along the lines of how we found electric fields via direct integration. We're going to begin by labeling a representative dq and labeling its distance r from the point at which we want to evaluate the electric potential. We then ask, does r vary with dq? And indeed it does, which means we will need to use a density to rewrite dq. And in this case, we have uniform density, so lambda is equal to Q over L is equal to dq by dl. And remember that because we're aligned along the x-axis, I can rewrite this as dq by dx. With that, I'm going to rewrite my integral. Integral K dq over R is equal to, I'll pull out the K, dq I'll rewrite as Q over L dx, so that we have integral dx over R. Now it's up to us to set where we want x equals 0 to be located. I'm going to choose it to be the point at which we are evaluating the field. And with that, that would mean that if I know the x coordinate of my dq, x is equal to r. So we got kq over L, integral dx over x. Lastly, our bounds of integration will be from the start of our rod, which is located at x equals a, to the end of our rod, which is located at x equals L plus a. What's our results? We get KQ over L natural log L plus a over a. Now that isn't the end of our problem. We were also interested in evaluating V of B minus V of A. Well, V of B is going to follow the exact same formulation, so we end up with KQ over L times natural log L plus B over B minus natural log L plus A over